Hi everyone, I'm Selim Sandal. I'll present our work adding RISC-V KVM acceleration to gem5. This lets gem5 boot full system RISC-V Linux with KVM. The motivation is straightforward. Some experiments need a complete Linux boot before reaching the workload region. If that boot runs entirely on a simulated CPU, it can dominate the experiment time. This is especially painful when the region of interest is short. x86 and ARM users already use KVM to avoid that cost. They run the early phase on the host CPU, then let gem5 take over for detailed simulation. We added the RISC-V version of that workflow. Before this work, gem5 already had a solid RISC-V full system path. Boards, DTB generation, Linux workloads, and M5 ops. gem5 also had a generic KVM infrastructure, but RISC-V did not have a KVM CPU model for full system Linux boot. For this work, we had to connect RISC-V architectural state to KVM, handle the CSRs and exits, integrate interrupts and timers, and make the boot path match how RISC-V KVM actually starts a guest. Our work central piece is RISC-V KVM CPU. It maps gem5's RISC-V CPU state onto a Linux KVM vCPU and exposes the path through the usual gem5 library CPU types.kvm interface. The board integration is also part of the feature. RISC-V board probes host KVM properties, emits guest visible platform information, uses direct Linux boot, and exposes M5 ops through an MMIO bridge. RISC-V KVM enters the guest in VS mode. The host kernel owns the hardware virtualization extension, and the guest Linux kernel does not start in machine mode. That means the normal OpenSPI boot path is not the right model here. gem5 prepares the initial guest state for supervisor execution and generates a platform description that matches the KVM vCPU. The same applies to ISA features. If the host KVM implementation does not expose an extension or vector state, gem5 cannot present that as a working KVM guest configuration. So you can see here the gray box is the gem5 user space process, the Python config builds the board creates the memory map and devices, and RISC-V KVM CPU controls the KVM vCPU and synchronizes state. The Linux KVM vCPU is in the host kernel. Guest instructions execute there. The platform is still gem5's responsibility. PLIC, UART, RTC, VirtIO block, M5 ops and simulation control remain in gem5. Guest MMIO exits come back to gem5 and gem5 injects device interrupts back into the guest. So KVM accelerates execution, but gem5 remains the platform model. So these are the major integration points. The CPU model connects base KVM CPU to RISC-V PC, integer registers, floating point state, CSRs, and optional vector state. Host negotiation uses KVM one-reg discovery to validate what the host kernel exposes. Board setup uses these properties to generate guest visible data. The boot path is direct to Linux boot. Devices and exits keep the same split as the previous slide. KVM handles in-kernel paths where possible, and gem5 handles simulated devices and M5 ops. RISC-V KVM CPU is the RISC-V implementation of gem5's KVM CPU interface. On the gem5 side, it owns the run loop, state transfer, and exit dispatch. On the KVM side, it creates a Linux RISC-V vCPU and accesses state through one reg. The implementation probes the host. It reads the KVM timer frequency, supported ISA extensions, vector length when RVV is enabled, and host CPU frequency for performance counter scaling. gem5 then uses those values to reject incompatible configurations early and to generate a DTB consistent with the KVM vCPU state. So state moves in both directions. Before entering KVM, gem5 writes PC, integer registers, floating point state, CSRs, and optional vector state through the RISC-V one-reg interface. When KVM exits, gem5 copies the state back, including supervisor status and interrupt-related CSRs. So after KVM execution, gem5 still has the architectural state needed for simulation control or detailed handoff. Privileged state is one of the RISC-V specific parts. The normal RISC-V full system path can model reset and machine mode firmware. The KVM path starts the Linux guest from supervisor execution. So gem5 has to translate initial privilege and CSR state into the view KVM exposes. For CSRs, some bits are managed by KVM and some are touched by gem5. The implementation preserves the KVM managed bits when gem5 updates the external interrupt state. External interrupts still come from the gem5 platform. The PLIC and simulated devices remain in gem5. When a device interrupt needs to reach the guest, gem5 updates the guest external interrupt state without clobbering KVM managed state. Timer and SPI related paths can stay in the host kernel when KVM supports them. That includes timer interrupts, IPIs, RFNs, HSM and PMU behavior. Guest time is also preserved across user space exits, so time accounting does not jump just because gem5 serviced an event. Some guest operations still exit the gem5 user space. Common SPI services can stay in KVM. Unsupported SPI calls return SPI error not supported. CSR exits are handled in gem5 when behavior is unsupported or visualized. One example is CSR seed, which gem5 emulates with deterministic entropy. Every exit is also a synchronization point, so gem5 brings the architectural state back before continuing. The KVM path uses direct Linux boot. gem5 loads the Linux kernel and generated DTB directly, the root file system is attached through virt.io, and boot arguments come from the gem5 workload object. The reason is privilege model. OpenSPI expects machine mode execution, while the KVM guest kernel runs in VS mode. Direct boot starts the guest in the mode KVM can provide, while gem5 still controls the platform description. The generated platform description is where the board and KVM vCPU meet. The DTB includes the CPU ISA information, cache block properties, KVM timer frequency, and vector length for when the RVV is enabled. The kernel command line passes the root disk, serial console, and M5ops MMIO window. So basically, Linux, the generated DTB, and the KVM vCPU should agree on what machine is being booted. For M5ops, we use the same address mode mechanism already used by other KVM-capable ISAs. x86 and ARM64 use address mode M5ops in util M5. The guest maps a small MMIO range through Gem5 bridge. A load from an M5op offset exits KVM back to Gem5. This is the right mechanism for KVM because Gem5 is not decoding every guest instruction while the host CPU is running the guest. So RISC-V now follows that model too. Gem5 bridge maps the range into the guest, and Gem5 decodes the MMIO address as hypercall, read file, or exit. M5ops provide the guest to Gem5 control path. The generated boot arguments expose the MMIO window to Linux, and guest code uses that window to report milestones. For the Ubuntu workload, M5 exits mark kernel boot completion, after boot script execution, and the final workload termination. That keeps the normal Gem5 workload structure even when the guest interactions are executing through KVM. From the user's side, the configuration follows the existing Gem5 library style. The processor is still a simple processor. The RISC-V specific part is selecting CPU types.kvm with isa.risc-v. The rest of the system composition stays normal. Board, cache hierarchy, processor and workload is still the same. The workload uses set kernel disk workload. For the KVM path, bootloader none selects the direct Linux boot that I mentioned. The kernel and disk resources target Ubuntu 24.04, and guest serial output still appears under M5out. So this is the command for the demo. We first build the RISC-V Gem5 binary, then run the Gem5 library RISC-V Ubuntu KVM configuration. During the boot, Gem5 creates the board and KVM vCPU, KVM executes the Linux boot on the host CPU, and Gem5 handles device exits, M5ops, and the workload completion. So this is the part where we'll do the live demo. I'll hopefully do this live, but if not, we'll send a video so the demo can be shown to you. So as you know, RV23 class RISC-V CPUs are appearing on the market more and more. Gem5 needed a RISC-V KVM path as well, so we hope this is useful for people running full system RISC-V workloads on Gem5. Thank you everyone for listening. If you have any questions, I can take them now.